investigation of the distribution and motion of galaxies reveals insights into the confounding nature of dark energy, a mysterious force that drives the accelerating expansion of the universe. In the particular context of the Andromeda system, a mysterious force that drives the accelerating captivating insight of the universe into the transient particular context of the Andromeda by examining the mysterious force individual stars provided captivating insight uncovers information in the particular context of the Andromeda by examining the mysterious force individual stars provided captivating insight uncovers information in the particular context of the Andromeda by examining the mysterious force individual stars provided researchers uncovers information in the particular context of the Andromeda by examining as well as its interactions with neighboring galaxies. Additionally, recent investigations by examining as well as its interaction of heavenly halo additionally bears similarities to our own Milky Way galaxy. This discovery has illuminated the dynamic nature of galaxies and the complex interactions between them. Observations and simulations suggest that a significant number of stars found in the outer regions of Andromeda's heavenly halo have migrated from small satellite galaxies that were gravitationally captured by Andromeda over time. Several dwarf systems merged with the Andromeda system, taking their heavenly populations with them. This process of cosmic cannibalism is known as cosmic gradual accretion or merger. Cosmic mergers are believed to be common in the universe and shape the structures and characteristics of galaxies, including Andromeda. The presence of stars from different galaxies resulting from interactions and mergers with smaller companion galaxies help scientists understand the kinematics and distribution of stars in the heavenly halos of galaxies like Andromeda and the Milky Way. By studying the populations of stars in these star halos, cosmologists can trace the history of cosmic mergers and interactions that have shaped these galaxies over billions of years. The heavenly halo contains stars that have been acquired by smaller satellite galaxies or star clusters, and their properties can provide valuable information about the history of galaxy mergers and assembly. This galaxy merger process has been a crucial factor in the evolution and development of galaxies like Andromeda and has contributed to the variety of features and structures observed in them. Through detailed observations and simulations, researchers can investigate the chemical structure, age, and motion of the stars that comprise the heavenly halos. This data allows them to reconstruct the timeline of cosmic mergers, identify the progenitor galaxies that contributed to heavenly populations, and understand the physical processes involved in such mergers. This approach is of utmost importance because should this immense universe ever come into contact with our own, it would be essential to be prepared with all available knowledge. The investigation of galaxies extends far beyond simply understanding their physical attributes and interactions. It delves into fundamental questions regarding the origins, structure, and destiny of the universe itself. One of the significant areas of interest is the role of galaxies in cosmic evolution. Galaxies are the building blocks of the universe, each serving as a lab for the study of star formation, black hole growth, and dark matter. Their formation and evolution can offer clues to the early states of the universe and the processes that have shaped its large-scale structure. Galaxies are not static entities. They are dynamic systems that evolve over time. This evolution is driven by various processes, including mergers, interactions with other galaxies, and internal dynamics. The study of cosmic mergers is particularly critical, as these events can trigger bursts of star formation, impact the growth of supermassive black holes, and reshape the structure of galaxies. The Milky Way itself has undergone several mergers throughout its history, and understanding these events helps researchers model its future interactions, including its impending collision with the Andromeda Galaxy. Recent research has also focused on the role of dark matter in cosmic evolution. Dark matter, an invisible form of matter that does not emit light or energy, is a critical component of the universe's mass. Its presence influences the structure and dynamics of galaxies, affecting their formation and evolution. Observations suggest that dark matter forms a halo around galaxies, influencing the rotational curves of galaxies and the distribution of visible matter. By studying the interaction between dark matter and visible matter in galaxies, scientists aim to better understand the nature of dark matter and its role in cosmic structure formation. Another key aspect of cosmic investigations is the assessment of cosmic feedback mechanisms. Feedback from star formation and supernova explosions can significantly influence the surrounding interstellar medium, affecting subsequent star formation and galaxy evolution. This process is essential for understanding how galaxies regulate their own growth and maintain their observed properties. High-resolution simulations and observations of nearby galaxies are helping to unravel the complexities of these feedback mechanisms, providing insights into how galaxies recycle gas and elements over time. The study of active galactic nuclei, AGN, is another exciting area of research. AGN are regions at the centers of certain galaxies where a supermassive black hole is actively accumulating material. The intense radiation and outflows from AGN can influence the surrounding galaxy, affecting star formation and the overall cosmic environment. By studying AGN, researchers gain insights into the growth of supermassive black holes and their impact on galaxy evolution. Observations of distant AGN provide a window into the conditions of the early universe, helping scientists understand the formation and development of galaxies in their infancy. The role of galaxies in the broader cosmic web is also a point of great interest. The universe is structured in a vast network of filaments and voids, with galaxies and galaxy clusters forming along these filaments. Understanding the distribution of galaxies within this cosmic web helps researchers study the large-scale structure of the universe and the influence of dark matter and dark energy on cosmic evolution. Large surveys such as the Sloan Digital Sky Survey, SDSS, and the upcoming Wide Field Infrared Survey Telescope, WFIRST, are designed to map the distribution of galaxies and investigate their role in the cosmic web in greater detail. Additionally, the study of galaxy clusters provides valuable information about the large-scale structure of the universe. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies. They are essential for understanding the distribution of dark matter and the effects of dark energy on cosmic evolution. Observations of galaxy clusters help scientists test the properties of dark matter, measure the rate of cosmic expansion, and study the growth of large-scale structures. Moreover, astronomical pursuits in cosmic investigations have significant implications for our understanding of fundamental physics. The study of extreme conditions, such as the interiors of galaxies and the regions around supermassive black holes, challenges the limits of our physical theories. Observations of these extreme environments can provide insights into the nature of fundamental forces and the behavior of matter under extreme conditions. The investigation of galaxies, therefore, intersects with high-energy physics, cosmology, and astronomy, contributing to a more comprehensive understanding of the universe. The advancement of observational technology plays a crucial role in expanding our knowledge of galaxies. Space telescopes such as the James Webb Space Telescope, JWST, offer exceptional views of the universe in various wavelengths, revealing insights about distant galaxies that were previously out of reach. Ground-based observatories equipped with advanced instruments such as the Very Large Telescope, VLT, and the Large Synoptic Survey Telescope, LSST, continue to provide valuable data on nearby and distant galaxies. The combination of these observational tools, along with theoretical models and simulations, enhances our ability to explore and understand the complex phenomena associated with galaxies. The exploration of galaxies is not only about observing their structures but also understanding their life cycles and interactions. The cosmic dance of merging galaxies can ignite new star formation, creating vibrant stellar nurseries. Research into the chemical enrichment of galaxies sheds light on how elements like carbon and oxygen are distributed throughout the universe, impacting the development of life-supporting environments. Furthermore, studying galaxy evolution informs our knowledge of cosmic timelines, helping astronomers piece together the universe's history. Each discovery fuels curiosity, urging scientists to refine their theories and seek answers to questions about dark matter, dark energy, and the ultimate fate of the cosmos. In summary, the investigation of galaxies encompasses a wide range of scientific inquiries, from their formation and evolution to their role in the cosmic web. By examining the physical properties, interactions, and feedback mechanisms of galaxies, scientists gain significant insights into the fundamental processes that shape the universe. The prevailing belief among most scientists is the Big Bang Theory, which stands as the leading explanation for the origins of the universe. This theory encompasses the creation of stars, planets, and all life on those planets, including ourselves. Despite its somewhat whimsical name, the Big Bang offers a descriptive glimpse into what might have occurred initially. The universe was once condensed into a minute space smaller than a pinhead, with particles densely packed. From this minuscule point, a colossal explosion of matter and energy occurred, known as the Big Bang. This event, occurring billions of years ago, sets the stage for the unfolding of cosmic history. However, advancements in scientific data have led to increasing contradictions with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever constructed, scientists anticipated that its observations would bolster the Big Bang theory. Regrettably, after just 1 year in space, the telescope astounded scientists with its unprecedented ability to peer deep into the universe's past. The James Webb Telescope's remarkable capabilities have unveiled galaxies dating back to a time so ancient that it challenges our understanding of the universe's origins. This revelation has sparked a fervent exploration into what existed before the Big Bang. One pivotal moment in this quest occurred when astronomer Rohan Natu, working with data from the telescope, stumbled upon a galaxy dating back a mere 300 million years after the Big Bang, making it the oldest galaxy ever observed. Nata's discovery sent shockwaves through the scientific community, underscoring the transformative potential of the James Webb Telescope. Its mission to revolutionize our comprehension of the cosmos has just begun, promising to unveil unprecedented insights into the earliest epochs of the universe's existence. This epoch, scarcely explored before, holds the key to understanding the formation of the first stars and galaxies. The telescope's findings have defied initial expectations, revealing galaxies with characteristics surpassing previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, challenging researchers to reconcile these observations with existing theories. As scientists grapple with these discoveries, they confront profound questions about the fundamental nature of the universe and the forces shaping its evolution. Furthermore, the James Webb Telescope's technology is revolutionary. Stationed 1.5 million kilometers away from Earth, it is shielded from terrestrial interference and cooled close to absolute zero by its tennis court-sized sunshade. The telescope carries a giant segmented mirror and exquisitely sensitive instruments designed to uncover details of cosmic dawn never before observed. This epoch, known as cosmic dawn, occurred no more than a few hundred million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process of how this unfolded remains a subject of intense study, with theories ranging from the influences of dark matter and dark energy to the interactions among starlight, gas, and dust. The telescope's observations of galaxies from cosmic dawn offer a unique opportunity for cosmologists to test their understanding of these underlying phenomena. By scrutinizing these ancient galaxies, scientists can either confirm the validity of their current models or uncover gaps in understanding that could lead to profound new discoveries. Initially, it was projected that the telescope would find only a few faint and small galaxies in its pilot investigations. However, the reality has far exceeded these expectations. The telescope's very first images of the distant universe revealed numerous galaxies with ages, sizes, and luminosities that surpassed all predictions. This unexpected bounty of early galaxies has triggered a race among astronomers to claim new records for the earliest known galaxies. Each day brings forth claims of yet another record-breaking discovery, leaving the scientific community in awe and prompting a re-evaluation of our understanding of cosmic history. In the wake of the James Webb Telescope's findings, theorists and observers have scrambled to explain the existence of these unexpectedly mature early galaxies. Some speculate that flaws in the analysis of the telescope's initial observations may be responsible for these anomalous discoveries. However, the consensus remains that these findings represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The recent revelations from the James Webb Space Telescope regarding early galaxies raise profound questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists speculate whether these observations can be reconciled with existing theories, others suggest that they might be the first indications that the universe is even more intricate and peculiar than previously imagined. At stake is nothing less than our fundamental understanding of how the orderly universe we know emerged from primordial chaos. The early findings of JWST have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant epochs and faraway galaxies, but also on the very existence of our own Milky Way galaxy. As Mark McCarran, Senior Advisor for Science and Exploration at the European Space Agency, aptly puts it, "You build these machines not to confirm the paradigm but to break it. You just don't know how it will break." The origins of JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, G. Winger, then Deputy Director of STSCI, was tasked with envisioning what would come after Hubble. Despite initial reservations, Winger and a small team began laying the groundwork for what would eventually become the next-generation space telescope, later renamed JWST after a former NASA administrator. Unlike Hubble, which primarily observes visible light, JWST was designed to observe in the infrared spectrum, allowing it to peer much deeper into the universe. This capability is crucial for studying early galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its large and cold star-like mirror, JWST became the ideal tool for unlocking the mysteries of cosmic dawn. The need for JWST was underscored in 1995 when the Hubble Deep Field observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope capable of delving even deeper into cosmic history. After more than 2 decades of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of science observations. Early programs like the Cosmic Evolution Early Release Science Survey and the GRISM Lens Amplified Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded predictions. The JWST observations have challenged existing notions about the early universe, revealing galaxies that defy conventional models. These unexpected discoveries underscore the importance of pushing the boundaries of scientific exploration and highlight the transformative potential of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to unravel the mysteries of the cosmos, they are poised to rewrite our understanding of cosmic history and the forces that have shaped our universe into what we see today. The early observations made by the James Webb Space Telescope have astonished astronomers by revealing extremely distant galaxies. Almost immediately prior to JWST, the most distant known galaxy was GNZ11, discovered in 2015 with a redshift of 11, corresponding to a cosmic age of about 400 million years. However, from the outset of JWST observations, the GLASS team, led by Rohan Natu and another independent group, made a remarkable discovery. They identified a galaxy dubbed GLASS Z13 at a redshift of 13, approximately 70 million years earlier in cosmic history than GNZ11. The rapid pace of these discoveries was facilitated by simplified techniques for estimating redshift, which, while less precise than direct measurements, provide a quick assessment of a galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass comparable to billions of suns despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Dozens of galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited disk-like structures, a feature not expected to manifest so early in cosmic history. Furthermore, evidence emerged for galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard cosmological model, lambda cold dark matter, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of such size and luminosity should not have formed so early in cosmic history. The emergence of massive galaxies in the early universe presents a significant puzzle for cosmologists to comprehend. To understand this dilemma, it is essential to grasp the early stages of the universe's evolution. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of cosmic evolution, from chaotic beginnings to the structured cosmos we observe today, is thought to have taken approximately 1 billion years. JWST observations challenged this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing numerous small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has detected galaxies that are already sizable and luminous. Follow-up observations with instruments like the Atacama Large Millimeter Array in Chile have provided further evidence supporting the authenticity of these distant galaxies, ruling out the possibility of low-redshift interlopers. These groundbreaking discoveries open new avenues for understanding the early universe and may necessitate revisions to our current cosmological models. JWST continues to revolutionize our understanding of cosmic history, challenging our preconceptions and pushing the boundaries of astronomical exploration. The absence of detectable dust in the observations made by the Atacama Large Millimeter Array underscores the challenges faced by telescopes in confirming observations made by the advanced capabilities of the James Webb Space Telescope. As Rohan Nata noted, while JWST can follow up on its own observations, ALMA's difficulty in detecting the galaxy highlights the intricacies of confirming such discoveries. The implications of JWST observations are profound, potentially challenging the canonical lambda-CDM cosmological model and necessitating revisions. Michael B. and Cullen expressed astonishment at the results, suggesting a significant departure from our current understanding of cosmology. One controversial theory that could explain these findings is modified Newtonian dynamics, which challenges the existence of dark matter and proposes alternative explanations for observed gravitational effects. JWST observations aligning with MOND predictions intrigue proponents like Mark McCluck, who sees this as further evidence supporting the theory. However, skepticism remains among some scientists, such as JACYP, who highlight the challenges in reconciling MOND with existing data. Alternatively, the absence of dust in early galaxies could offer a simpler explanation for their brightness, potentially confounding efforts to accurately measure their masses. Andrea Ferrara suggests that dust may not have had enough time to form in the early universe or may have been expelled during galaxy formation. Charlotte Mason and her colleagues proposed that JWST may be primarily detecting the brightest young galaxies, which are easier to spot. David Spergel suggests that efficient high-mass star formation in the early universe could explain the observed brightness of these galaxies. He theorizes that early magnetic fields may have played a role in kickstarting star formation, offering a potential explanation for the rapid emergence of galaxies in the early universe. The rapid influx of scientific papers stemming from JWST's initial observations underscores the significance of these findings and the profound implications they hold for our understanding of cosmology. As scientists continue to analyze JWST data, they may uncover further insights that challenge and expand our understanding of the universe. When the first data began streaming down from the James Webb Space Telescope, astronomers were eagerly anticipating the results. Many had been working on their data analysis pipelines for years in preparation. Instead of following the traditional peer review process, which can often take months, astronomers opted to publish their findings on AR14, a website where scientific papers can be uploaded after minimal review by moderators, but well before formal peer review. This approach allowed for a new form of peer review to unfold in near real time on platforms like Twitter and other social media channels. Rohan Natu describes it as science by arrival, and the resulting frenzy of discussion was intense and surprising. Nancy Levinson, the interim director of STSCI, admits underestimating the magnitude of the activity. However, there are concerns about the potential drawbacks of this rapid dissemination of findings. Klaus Pontypool, JWST project scientist at STSCI, notes that while the swift sharing of results allows for quick publicization and discussion, there's a risk of rushing the process. Actually, we got a gander at some amazing pictures as the Webb peers back around the start of everything. The James Webb Space Telescope, JWST, has uncovered a disclosure that challenges the surface of our understanding. This new discovery has incited the interest of stargazers and scientists, suggesting a potentially enormous event that might change the universe to the extent that we may be concerned. The finding is significant to the point that it raises questions about the reason for our galactic presence. Could this disclosure sooner or later lead to the end of all we know? Is the universe close to the actual edge of a remarkable event beyond our current understanding? Join us as we examine the latest revelation of the James Webb Telescope and how it could shape the universe. When we investigate the universe's edge, we start with the perceptible universe. It's like seeing through a window into the area past the discernible universe. The discernible universe includes all that we can now perceive, measure, and investigate with our telescopes and space missions. It is a collection of stars, galaxies, and celestial bodies that are recognizable to us. However, the conspicuous universe is essentially a piece of the whole universe, a piece of a massive, immense pie that individuals can study and see. Yet, the general size and kind of the universe remain a secret. The width of the perceptible universe is around 93 billion light-years. This figure is the result of various factors, including the distance that light can travel in one Earth year, 9.46 trillion kilometers or 5.88 trillion miles. A light year is the distance traveled by light, the fastest thing in the universe in 1 year. The estimated age of the universe since the Big Bang is 13.8 billion years. This means that light emitted by objects in space that we can see has been traveling toward Earth for nearly 13.8 billion years. That suggests that the visible universe is 13.8 billion light-years in every direction from Earth and 27.6 billion light-years in diameter. However, Hubble's observations indicate that space has been expanding since the Big Bang. Therefore, the visible universe has been growing. Estimates of this expansion show that objects that emitted light 13.8 billion years ago from a distance of 13.8 billion light-years are now significantly farther away from Earth, around 46 billion light-years away. This shows that the discernible universe expands more than 46 billion light-years in each direction from Earth and has a diameter of around 93 billion light-years. So when we say the visible universe's breadth is 93 billion light-years, we're talking about an incredible reach from around 13.8 billion years ago in an extraordinarily expansive impact. This impact started what we now refer to as the ongoing expansion. Since that pivotal moment, the universe has not only been expanding but has also been accelerating. Frustrating forces like the mysterious dark energy seem to be driving the speed increase, pushing the universe's limits ever further apart. Matter began to form under the pull of gravity as the universe expanded. This gravitational attraction pushed particles together, resulting in the formation of complex structures such as stars, galaxies, and eventually planets like our own dear Earth. Given the universe's constant expansion, the visible universe extends by another light-year each Earth year. At the same time, light from farther objects continues to reach Earth. Interestingly, this means that we are seeing progressively more of the universe as time passes. While we will always be unable to observe the entire universe from Earth, the field of observation is continually growing. Advances in technology capture and investigate electromagnetic radiation beyond the visible range, allowing us to discover and view distant individual galaxies, clusters, and superclusters in the visible universe. Specific telescopes like radio telescopes, X-ray telescopes, ultraviolet telescopes, infrared telescopes, and others have been valuable in this regard. The renowned Hubble Space Telescope and James Webb Space Telescope have enabled the observation of the first stars and galaxies that emerged in the observable universe, making these wonders more accessible to the public. Despite its vastness, the universe is remarkably empty. Even if we reduced our entire solar system to the size of a quarter, the nearest star would still be around 2 soccer fields away. This vast emptiness extends within our own Milky Way galaxy, which is one of billions in the observable universe, providing us with a sense of its immense scale. You may be wondering why we can't just see everything in the universe. There are several explanations for this limitation. Despite the fact that light is the fastest object in the universe, it still takes time to travel through space. This means that when we look at distant objects, we are essentially looking back in time. The farther away an object is, the longer its light has taken to reach us. It's like looking through an enormous time machine, unwinding the history of our universe as we witness galaxies millions, if not billions, of light years away. However, there is another factor at play. The universe is expanding. Consider the surface of an inflated balloon covered in dots. The dots move apart from each other as the balloon grows. The universe follows a similar rule. Galaxies drift away as the fabric of space stretches. The light emitted by distant objects undergoes a change known as redshift. Because of this expansion, light wavelengths are stretched, with objects moving away shifting to longer wavelengths, which are generally perceived as a reddish color. Some celestial bodies eventually pass beyond a critical distance known as the cosmic horizon, where their light is too far away to reach us due to the universe's expanding nature. Given these two crucial factors, the light's journey through time and the expansion of the universe, it's not surprising that we haven't seen the whole universe yet. Indeed, even with the most advanced telescopes and technology, our vision remains constrained by the fundamental characteristics of the universe. We must delve a bit more into these concepts. The universe's size is astonishing. Scientists use measurements like light years to represent the distance that light travels in a year, roughly 5.88 trillion miles or 9.46 trillion kilometers. Our universe, the Milky Way, is nearly 100,000 light-years across. Even within our galaxy, the closest star to our Sun, Proxima Centauri, is about 4.2 light-years away. When we explore space, we can see galaxies billions of light-years away. This means that the light we see from those galaxies started its journey billions of years ago, giving us a glimpse into the universe's early history. The mystery of the universe's edge and the quest to understand its possible boundaries or limits have attracted the attention of many people from various fields. While definitive answers continue to elude us, three significant theories have emerged, each offering a unique perspective on the vastness of space. The first theory suggests that the universe is infinite, with no definitive end. This idea aligns with the cosmological principle, which states that the universe is isotropic. Its uniformity and appearance are the same from every vantage point. If this theory is true, it implies that the universe has no limits and can extend infinitely in all directions. Investigating these theories generates both scientific and philosophical interest. The concept of an infinite universe challenges our ideas about space and our perception of its boundlessness. On the other hand, a finite universe without an edge challenges our notions of limits and boundaries, suggesting the possibility of recurring patterns within the fabric of space. The multiverse hypothesis, with its parallel universes, offers a rich landscape for exploration, proposing the existence of realms vastly different from our own. If true, it could imply that variations in physical laws and fundamental constants might lead to entirely different forms of existence, opening up a vast expanse of possibilities beyond our current understanding. However, these ideas remain hypothetical and elusive. Investigating the universe's edge presents significant challenges. It is difficult to definitively prove or disprove these theories due to the vastness of space and the limitations of our current observational tools and technology. The quest to uncover the universe's edge has been a fascinating journey rich in theories and reflections. Yet one remarkable instrument, the James Webb Space Telescope, JWST, stands out as a promising sign, revealing insights into the mysteries that shroud the universe's origins. This incredible instrument has the potential to uncover our universe's hidden history, allowing us to gain knowledge far beyond what was previously imagined. The JWST is a technological marvel, specifically designed to observe the universe with unmatched precision. Its remarkable features enable us to peer into the universe's beginnings. The JWST has discovered massive galaxies dating back between 500 million and 700 million years after the Big Bang. According to recent research published in Nature, these ancient galaxies challenge predictions with sizes significantly larger than expected for their age. These astonishing discoveries cast doubt on established theories about galaxy formation and evolution in the early universe. Astronomers initially expected to observe small, young galaxies during the telescope's observations. Instead, they were surprised to find these enormous massive structures, which have reshaped the narrative of cosmic evolution. The development of these ancient galaxies is particularly astounding, contradicting prevailing theories. These cosmic giants have reached a level of development comparable to our 13-billion-year-old Milky Way. According to Dr. Lear, the principal investigator of the study, This finding challenges our understanding and opens the door to a new perspective on how galaxies formed in the early universe. Moreover, the JWST has recorded light from the universe's earliest stars, taking us back to when the universe was just 300,000 years old. These early stars, known as population 3 stars, have very distinct properties. They formed when the universe was essentially composed of primordial elements like hydrogen and helium, with minimal traces of heavier elements. Unlike contemporary stars, population 3 stars lacked heavier elements, leading to a brighter and more intense light output. These ancient stars could provide crucial information about the formation of galaxies and the chemical evolution that followed. One of the significant discoveries of the JWST is the observation of 13-billion-year-old galaxies whose shapes and structures are strikingly similar to our Milky Way. These galaxies act as time capsules, preserving the universe's early stages. Their surprising similarity to our own galaxy challenges previous assumptions about the early universe's chaotic and violent nature. According to Dr. Lear, the JWST observations have completely revised our understanding of the early universe. These discoveries suggest that some galaxies achieved a high level of development and structure in a relatively short time. Such findings not only stir doubts about existing models of galaxy formation, but also invite us to reconsider our views on the complexity and diversity of cosmic evolution. As we explore the vast waters with the James Webb Space Telescope, each observation opens up new vistas of knowledge. This pioneering instrument continues to unveil the mysteries of the universe's edge, allowing us to grasp our cosmic origins in remarkable ways. The JWST has undoubtedly revolutionized astronomy, pushing the boundaries of human knowledge and expanding our grasp of the immense universe that extends beyond our comprehension. The James Webb Space Telescope represents a significant leap forward in our ability to probe the depths of existence. Its advanced capabilities, including its large primary mirror and array of scientific instruments, enable observations that were previously beyond our technological reach. Located at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, the JWST operates in a region where it can maintain a stable orbit and avoid interference from Earth's heat and light. One of the JWST's key missions is to study the formation of stars and galaxies in the early universe by detecting infrared radiation, which can penetrate cosmic dust and reveal celestial objects obscured from visible light. The telescope can capture images of galaxies that formed shortly after the Big Bang. These observations provide valuable insights into the conditions and processes that led to the formation of the first galaxies and stars. The telescope's ability to analyze the light from distant objects also allows astronomers to study the chemical composition of galaxies across cosmic time. By examining the spectral signatures of elements present in these ancient galaxies, scientists can trace the evolution of chemical elements from primordial hydrogen and helium to the heavier elements created in stellar interiors and distributed through supernova explosions. Additionally, the JWST plays a crucial role in studying planetary systems beyond our solar system, known as exoplanets. By utilizing its powerful instruments to analyze the atmospheres of exoplanets, the telescope contributes to our understanding of their potential habitability and the processes governing their formation and evolution. This research is essential for addressing the age-old question of whether life exists beyond Earth. Beyond its scientific achievements, the JWST represents a triumph of international collaboration and engineering ingenuity. Developed through a partnership between NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA), the telescope embodies the collective commitment of the global scientific community to advancing our understanding of the universe. The development of the JWST was not without challenges. Initially proposed in the 1990s as the successor to the Hubble Space Telescope, the JWST faced numerous technical and financial hurdles that delayed its launch by several years. However, the perseverance of scientists, engineers, and managers eventually paid off with the successful launch of the telescope in December 2021. Looking ahead, the JWST promises to continue transforming our comprehension of the universe. Its extraordinary sensitivity and resolution will enable astronomers to observe the faintest and most distant objects in the universe, shedding light on some of the most profound questions in astronomy. These include the nature of dark matter and dark energy, the formation and evolution of galaxies, and the origins of planetary systems. Something is amiss in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions. How fast is the universe expanding? For more than a decade, two types of measurements have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hoped that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the question once and for all. But consensus has so far failed to materialize. Instead, the Space Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate. An exciting and interesting possibility is that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with a bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then the young cosmos was formed. An expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime. A small fraction of this matter safely escaped from the fry as the universe inflated like a balloon. The standard story goes that ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density, and therefore its expansion rate, decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter, lambda CDM, model of cosmology, which maps the growth of the cosmos and predicts its end with matter eventually spread so thin that it experiences a heat death called the Big Freeze. Many of the model's predictions have been proved to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is that we don't understand the last two. But an even greater threat to the lambda CDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than lambda CDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little more than a radar gun." The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be formed. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant, or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will recede from us and us from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables. Dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. Wendy Friedman, an astrophysicist at the University of Chicago, said the next rungs are added using Cepheid readings alone. Then astronomers look at the distances of the stars and supernovae on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec. When compared to the Planck measurement, however, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovae, another standard candle because they all burst at the same absolute luminosity in remote galaxies, Rees and his colleagues arrived at a nearly identical result: 73 kilometers per second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ronan Kai, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision and the Cepheid distance ladder measurement is getting close to 1%. So a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmology into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, An official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who discovered evidence for dark matter, said at the time, "Nobody wanted to let go of their toy. All of the people involved believed so strongly in their own results and so strongly in the fact that their observations and their measurements were done correctly. It just left people wanting to figure out how to explain this." In February 2023, with James Webb and another independent Hubble Distance Ladder result confirming the Hubble tension, cosmologists were left with three possible explanations: measurement errors, new physics, or some combination of the two. Kai explained that most of the data supports new physics. The simplest and most popular hypothesis is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe look smaller when we look back in time to the early universe, making the expansion rate appear faster today. There are other explanations, such as the possibility that there are two kinds of dark energy or that dark matter interacts with light, but these explanations introduce complexities that cosmologists are wary of. Without further data, dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology enabled it to see galaxies formed just 300 million years after the Big Bang. However, while peering at the universe's origins, astronomers found that these primordial galaxies are far more massive and evolved than the standard model predicts. Early galaxies should have been full of young, hot stars forming at breakneck speed, but James Webb showed many of them were bursting with heavy elements from earlier generations of stars and actively building up bulging cores of supermassive black holes. James Webb's observations have intensified the debate in cosmology by providing precise data that confirms existing discrepancies and reveals unexpected details about early galaxies. Resolving the Hubble tension and understanding these early galaxies might require new physics or a significant revision of the standard cosmological model. The pursuit of these answers is one of the most exciting frontiers in modern astrophysics. The James Webb Space Telescope, JWST, has not only revolutionized our understanding of early galaxies, but has also opened new avenues for exploring fundamental questions in cosmology. Its infrared capabilities allow it to peer deeper into the universe than ever before, capturing light from some of the earliest galaxies formed just 300 million years after the Big Bang. These observations have challenged the conventional wisdom about galaxy formation, suggesting that early galaxies were not just simple young structures but were surprisingly mature, containing heavy elements and harboring supermassive black holes at their core. This discrepancy between theory and observation raises profound questions about the mechanisms driving galaxy evolution in the early universe. It hints at processes that were perhaps more rapid and efficient than previously thought, leading to the formation of galaxies with unexpectedly complex structures so soon after the Big Bang. Moreover, JWST findings have exacerbated the long-standing puzzle surrounding dark matter and dark energy. These elusive components, comprising the majority of the universe's content, remain poorly understood. Dark matter, which interacts gravitationally but not electromagnetically, plays a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts, its precise nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. On the other hand, dark energy, responsible for the accelerated expansion of the universe, presents an even more enigmatic challenge. The standard cosmological model posits dark energy as a cosmological constant, consistent in its properties throughout spacetime. However, discrepancies such as the Hubble tension suggest that dark energy's behavior may not be so uniform. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially influencing the universe's expansion rate differently at various epochs. Solving these mysteries requires not only advanced observational capabilities like those of JWST, but also theoretical frameworks that can accommodate new data without abandoning the successes of the current model. Astrophysicists and cosmologists are exploring various hypotheses, from modified gravity theories to exotic particles and interactions beyond the standard model of particle physics. The implications of JWST discoveries extend beyond cosmology into broader astrophysical questions. including the origins of life-supporting planets and the conditions necessary for complex chemistry to arise in the universe. The observable universe refers to the portion of the universe that we can observe and study using telescopes and other scientific instruments. However, our ability to observe is limited by the nature of light, which serves as the primary source of information about the cosmos. Light travels at a finite speed, meaning it takes time to reach us from distant objects. This creates a boundary on what we can observe, as we can only see objects and events within a certain distance. This boundary is often referred to as the observable universe, which doesn't mean it's the total size of the universe but just the part we can currently detect with our technology. Moreover, this boundary is determined by the amount of time that light has had to travel since the universe began. Since we are observing light that has traveled from very distant objects, we are actually seeing those objects as they were in the past, not as they are now. The diameter of the observable universe is estimated to be about 93 billion light-years, which is considerably larger than the estimated age of the universe, 13.8 billion years. This discrepancy arises because the universe is expanding, causing objects to move away from each other. As a result, light from some of these objects takes longer to reach us. The universe is a vast and enigmatic space, and although we have gathered significant knowledge, there remains much that we have yet to discover. The James Webb Telescope, along with other advanced instruments, offers new opportunities to expand our understanding of the universe's structure, composition, and history. These tools allow us to delve deeper into cosmic phenomena that have remained mysterious for centuries, unveiling new layers of complexity in the cosmos. What lies beyond the observable universe is one of the most profound questions in cosmology. To explore the farthest reaches of the observable universe, we would require transportation methods that surpass current human technology. Concepts such as wormholes or distortion engines, which could theoretically allow us to bend space and time, have been proposed as possible solutions for such a task. However, these ideas are still hotly debated among scientists, many of whom argue that faster-than-light travel is impossible, as it contradicts the laws of physics as we currently understand them. Despite these challenges, the idea of breaking the light-speed barrier remains a subject of fascination. Even if such technologies could one day become a reality, they would necessitate advancements in machinery and a deep understanding of the fabric of the universe, both of which are currently beyond human capabilities. The theory of cosmic inflation, which suggests that the universe expanded exponentially just after the Big Bang, proposes that the actual size of the universe is vastly larger than the observable part. In fact, it may be at least \10⁻23 times larger than the region we can observe. This number is so enormous that it is almost impossible for the human mind to grasp. While we can only see a small part of the universe, scientists continue to speculate about what may lie beyond the observable limits. Theories about unobservable regions are built upon the data we have gathered from studying distant galaxies, and NASA plays a critical role in this effort. NASA, in collaboration with other space agencies and research institutions around the world, has made numerous significant contributions to our understanding of the universe. Even before the James Webb Telescope became operational, NASA had already published images of the ultra-deep field obtained with the Hubble telescope. When the James Webb Telescope made its debut, it was used to observe the most distant galaxies ever recorded. These images revealed the presence of numerous galaxies shining in the distant cosmos, appearing as they were millions of years after the Big Bang occurred approximately 13.8 billion years ago. The expansion of the cosmos causes the stretching of light to redder wavelengths, which allows the James Webb Telescope to detect infrared light. This has enabled us to observe galaxies forming in the early stages of the universe's history. The James Webb Telescope has made observations of several fields of distant galaxies, allowing scientists to study the rate at which stars formed in the early universe. These data revealed the existence of a significant population of galaxies that were forming stars in those early stages. The discoveries are truly fascinating and thought-provoking. For a long time, humans have contemplated the possibility that we are alone in this vast universe. However, these new determinations within the observable universe lead us to believe that there must be millions of galaxies in the unobservable part of the universe. This idea is truly shocking and awakens a sense of awe and wonder about the vastness of the cosmos. are there extraterrestrial beings somewhere in the universe? The likelihood of life beyond Earth has never been more compelling, leading us to consider the possibility of the existence of extraterrestrials. There are numerous planets outside our solar system known as exoplanets, which have been discovered using techniques such as the transit method and the radial method. Some of these exoplanets may have Earth-like characteristics and harbor life. This theory has been supported by another discovery made thanks to the James Webb Telescope related to the exoplanet JWST 96b. This planet is located outside our solar system, and its light spectrum reveals something surprising: the presence of water molecules. Additionally, the spectrum shows signs of haze and clouds, which were not previously thought to exist on a habitable planet. Based on habitable environments found elsewhere in the universe, and considering advances in the search for exoplanets, it is difficult to rule out the possibility that alien beings exist beyond our planet. Although we do not yet have conclusive proof, discoveries and evidence suggest that the existence of extraterrestrial life is a fascinating possibility. What about the multiverse in relation to the vastness of the observable universe? The possibilities are endless. The concept of the multiverse, also known as the many worlds interpretation, is a theoretical idea in physics and philosophy that suggests the existence of multiple parallel universes or dimensions beyond our own. The multiverse is mainly discussed in the context of quantum physics, which deals with the behavior of tiny particles such as atoms and subatomic particles. According to some interpretations of quantum physics, the act of observation can cause a quantum system to collapse into a single state. However, in the many worlds interpretation, the act of observation simply causes the system to split into multiple states, each representing a different outcome. It is important to note that the idea of the multiverse remains highly speculative and is not yet supported by conclusive evidence. Therefore, it is difficult to state with certainty whether it is a valid concept or not. Some scientists and philosophers find the idea of the multiverse intriguing and potentially useful in explaining certain phenomena, while others are skeptical about its validity. Given that we do not know what lies outside our universe, the possibility of the existence of a multiverse remains as valid as the famous Schrödinger's cat thought experiment or the nature of dark flow. It is a concept that arouses fascination and reflection but requires further research and evidence to be confirmed. Thus, the phenomenon known as dark flow exists. The question is complex and raises an intriguing issue. Dark flow emerged in 2008 as a possible explanation for the observation that some galaxy clusters appear to move faster than expected based on the distribution of matter in the universe. The concept of dark flow suggests that these galaxy clusters may be influenced by some form of dark matter or dark energy that pulls them in a specific direction. However, the existence of dark flow remains controversial and has not been accepted by the scientific community at large. Some studies have suggested that dark flow may be real and could be caused by the presence of a massive structure in the universe that exerts an attraction on galaxy clusters. However, other studies have failed to confirm the existence of dark flow and have proposed that the observed motion of galaxy clusters could be the result of other factors, such as systematic errors in the detected galaxies. While some studies suggest its possible existence, we cannot state with certainty its presence outside the observable universe. More research and evidence are needed to better understand this intriguing phenomenon. As we delve deeper into the mysteries of the universe, we encounter the concept of dark matter, which constitutes about 27% of the universe's total mass energy content. Despite being undetectable by conventional means, its presence is inferred through gravitational effects on visible matter, such as galaxies and galaxy clusters. This elusive substance plays a crucial role in the formation and structure of the universe. The behavior of galaxies suggests that they are surrounded by vast halos of dark matter holding them together, despite the visible matter being insufficient to account for their gravitational binding. One of the most compelling pieces of evidence for dark matter comes from observations of galaxy rotation curves. When astronomers measure the rotational speeds of galaxies, they find that stars on the outskirts rotate at speeds that do not decrease as expected based on the visible mass. Instead, they maintain higher velocities, indicating the presence of unseen mass. This has led to the development of various dark matter theories, including weakly interacting massive particles, WIMPs, and axions, which are hypothetical particles that could make up dark matter. Additionally, The concept of dark energy has emerged as a dominant force influencing the universe's expansion, accounting for approximately 68% of the universe. Dark energy is thought to be responsible for the observed acceleration in the expansion rate of the universe. This was a groundbreaking discovery made in the late 1990s through observations of distant supernovae. As galaxies move apart, dark energy acts as a kind of anti-gravity, counteracting the attractive force of gravity on cosmological scales. Researchers are continuously investigating the nature of dark energy, and several theories have been proposed. One of the leading hypotheses is the cosmological constant introduced by Albert Einstein in his equation of general relativity. Another possibility is quintessence, a dynamic form of dark energy that changes over time. Understanding dark energy is crucial for comprehending the ultimate fate of the universe, whether it will continue expanding indefinitely, halt, or eventually reverse into a big crunch. In addition to these mysteries, the study of cosmic background radiation provides valuable insights into the early universe. The cosmic microwave background, CMB, is a faint glow left over from the Big Bang, permeating the universe. Detailed measurements of the CMB have revealed important information about the universe's age, composition, and curvature. Analyzing fluctuations in the CMB helps cosmologists understand the distribution of matter and energy in the early universe, allowing us to piece together the evolution of cosmic structures over billions of years. Moreover, the study of gravitational waves, first detected in 2015 by the LIGO Observatory, has opened a new window into the universe. Gravitational waves are ripples in spacetime produced by accelerating massive objects, such as merging black holes or neutron stars. Their detection provides a novel way to observe cosmic events that are not accessible through traditional electromagnetic radiation like light. This new observational technique is revolutionizing our understanding of astrophysical processes and the nature of gravity itself. The interplay between black holes and galaxies also captures significant attention in contemporary astrophysical research. Supermassive black holes, which reside at the centers of most large galaxies, are believed to have a profound impact on their host galaxies' formation and evolution. The relationship between black hole growth and galaxy evolution remains an active area of study, with many questions surrounding how these massive entities influence star formation rates and the distribution of galactic matter. In recent years, the discovery of exoplanets has exploded, with thousands of planets identified outside our solar system. These findings, particularly through missions like Kepler and TESS, Transiting Exoplanet Survey Satellite, have sparked intense interest in understanding planetary systems and the conditions necessary for life. Scientists study the atmospheres of exoplanets using transit spectroscopy, searching for signs of habitability such as water vapor, methane, and other biosignatures. The search for extraterrestrial life extends beyond just finding potentially habitable exoplanets. Missions like the Mars rovers have been instrumental in examining the geology and climate of our neighboring planet. Evidence of ancient riverbeds and minerals that form in the presence of water suggest that Mars once had conditions suitable for life. Similarly, moons like Europa and Enceladus, with their subsurface oceans, are prime targets in the quest for microbial extraterrestrial life. As we explore these celestial bodies, the field of astrobiology emerges as a multidisciplinary effort that combines aspects of biology, chemistry, and planetary science to understand the potential for life elsewhere in the universe. This research aims not only to find life, but to understand how life might arise and evolve in different environments. Lastly, the philosophy of cosmology invites us to consider the implications of our findings. Questions about the nature of reality, the meaning of existence, and humanity's place in the cosmos are profound and far-reaching. As we gather more data and develop new technologies, we must also contemplate the ethical dimensions of our explorations, including the potential consequences of contacting extraterrestrial life and the stewardship of our home planet in the context of a vast interconnected universe. In conclusion, the journey through the cosmos is filled with complexity and wonder. From the search for dark matter and dark energy to the discovery of exoplanets and the study of gravitational waves, each revelation brings us closer to understanding the universe and our place within it. As we continue to explore and push the boundaries of knowledge, we are reminded of the infinite mysteries that await us in the cosmos. Diving into the vessel of space, there is an extraplanet called Proxima b that has a makeup very similar to Earth and is located in the habitable zone of its star, Proxima Centauri. This star is notable for being the closest star system to our own, after the Sun. This red dwarf star is situated 4.23 light-years away from our Sun, making it a fascinating target for astronomical studies. The fact that Proxima b has conditions resembling those on Earth piques the interest of scientists and enthusiasts alike. Recently, advancements in technology, particularly the new James Webb Space Telescope, have enabled astronomers to detect light emanating from the exoplanet Proxima b. This discovery could serve as compelling evidence that the planet is inhabited by extraterrestrials, igniting excitement and curiosity about the possibilities of life beyond our planet. However, this finding is just one of the numerous exciting discoveries that the James Webb Space Telescope could offer us. As we explore what our new telescope may uncover on Proxima b, it raises important questions about the feasibility of sending a manned mission to this distant exoplanet. Stay tuned as we delve deeper into this mysterious discovery by the James Webb. If you're passionate about keeping up with the latest developments in the universe and its myriad wonders, consider subscribing to our channel. Don't forget to like this video and turn on the notification bell to stay informed. Now, what exactly is an exoplanet? An exoplanet is defined as a planet that orbits a star other than our Sun, which means it exists outside the boundaries of our solar system. Among the exoplanets scientists have been researching, none have drawn as much interest as Proxima b. The star associated with this exoplanet, Proxima Centauri, is classified as a red dwarf, characterized by its relatively cool temperature of 2,872 degrees Celsius. It is significantly less massive than our Sun and is only about 500 times less luminous. The proximity of Proxima b to its star is crucial because it lies within the habitable zone, where conditions may be suitable for life as we know it. This zone is typically where liquid water can exist on a planet's surface, a key ingredient for life. Proxima b has features that are remarkably Earth-like, including continents, oceans, and potentially even life itself. The presence of auroras could give the planet a greenish hue in its atmosphere, resulting from intense flares emitted by its star. These stellar flares create a complex magnetic environment that might foster unique atmospheric phenomena. Interestingly, Proxima b is tidally locked, meaning the same side of the planet always faces its star, similar to how our moon orbits Earth. This results in a twilight zone where conditions might be more favorable for life. The surface temperature on Proxima b could range from -90 degrees Celsius to 30 degrees Celsius, creating a wide array of environments. Completing one full orbit around Proxima Centauri takes approximately 11 Earth days, indicating a much shorter year than we experience on Earth. Additionally, Proxima b has a gravity that is about 1.3 times greater than that of Earth, which would have implications for any potential life forms that may develop there. However, scientists remain uncertain about the exact nature of Proxima b's atmosphere. If it exists, it may contain essential ingredients such as carbon dioxide, various minerals, and water, all vital for the biochemical cycles necessary for life. Despite the excitement surrounding Proxima b, sending manned missions there remains a significant challenge due to the vast distance involved. Nevertheless, a project known as Breakthrough Starshot is under development, supported by billionaire Yuri Milner. This project aims to create nanoprobes capable of traveling at 20% the speed of light. These probes would be designed to visit Proxima Centauri, offering an unprecedented opportunity to study our neighboring star system up close. The proposed speed of these nanoprobes is around 16,000 kilometers per second, which would allow them to reach Proxima Centauri in a few decades. Such a mission could provide invaluable insights for future generations, unlocking secrets about Proxima Centauri and its intriguing exoplanet, Proxima b. So what might these nanoprobes uncover when they finally arrive? Interestingly, we have already begun receiving signals from Proxima Centauri. These signals were detected by the Parkes radio telescope during investigations into the star, which was emitting unusually strong flares that captured the attention of astronomers, including Anderson from the University of California. He led the Breakthrough Listen project, which aims to search for technological civilizations in space, furthering our quest to understand if we are alone in the universe. This initiative is part of the broader search for extraterrestrial intelligence, commonly known as SETI. The project involves the collection and storage of various signals from space, creating a database for future research. The data collected has led to significant discoveries, particularly when Shin Smith, a diligent college student at UC Berkeley, started analyzing the signals during his work. He stumbled upon a curious narrowband radio frequency emission at 982.000 MHz, which was hidden within the observations of Proxima Centauri. This exciting discovery caught the attention of Sophia Schick from Penn State University, who took over the signal analysis. She remarked that this particular signal represents one of the most thrilling finds of the Breakthrough Listen project, as it deviates from typical patterns we have observed before. The Parkes radio telescope operates by detecting signals over 53-minute periods. During these sessions, the telescope points at Proxima Centauri and then switches to observe other areas of the sky to confirm that any potential signals originate from the star itself. Sophia explained that during approximately 3 hours of observation, a signal consistently returned during 5 of the 30-minute intervals when the telescope was aimed at Proxima. Conversely, when the telescope moved away, the signal vanished, raising intriguing questions about its source. This reinforces the significance of the discovery. Astronomer Darcy Wright of the University of Pennsylvania highlighted that observing this type of signal, which doesn't come from Earth, strongly suggests the presence of advanced technology. Ongoing analysis of these signals aims to confirm their extraterrestrial origin, with the assistance of the James Webb Space Telescope, which is being directed towards Proxima b. Scientists believe it may soon detect artificial light from the planet, providing additional evidence of a possible civilization. Abraham Loeb from Harvard University emphasized that if Proxima b emits artificial nighttime illumination reaching 5% of the natural daytime illumination, the James Webb could detect this light with an 85% certainty, which would be groundbreaking. Proxima b is significantly smaller and dimmer than our Sun, which affects the configuration of its habitable zone. This unique characteristic means that the habitable zone is much closer to the star than it is in our solar system. Proxima b orbits at a distance of approximately 4.5 astronomical units from Proxima Centauri, leading to an orbital period of about 11.2 Earth days. Proxima Centauri is known for its active nature, producing violent solar flares that could pose challenges to the potential habitability of Proxima b. Additionally, the exoplanet's close proximity to its star results in extreme temperature variations, with the daytime side being scorching hot and the nighttime side freezing cold. These drastic temperature changes could have profound implications for the planet's ability to support life. Proxima b stands out as the exoplanet that captivates the attention of astronomers and researchers due to the wealth of data gathered about it. However, it is not the only exoplanet that exhibits Earth-like conditions that may support life. Within the Milky Way galaxy alone, a total of 55 potentially habitable exoplanets have been confirmed, with many more yet to be discovered. As our technology advances, we continue to search for and identify these distant worlds. For instance, in our neighboring Andromeda galaxy, which has dimensions comparable to our own, there remains vast potential for habitable or inhabited planets. Moreover, within the larger structure of the universe, superclusters of galaxies present even more possibilities. The Milky Way belongs to the Local Group, a cluster of about 40 galaxies, which is itself part of the local supercluster containing roughly 100,000 galaxies. Remarkably, estimates suggest that there are around 10 million superclusters throughout the universe. This leads to profound contemplation. If the Milky Way is relatively modest in size and already has 55 confirmed potentially habitable planets, just imagine the countless habitable planets or even those hosting life across the infinite expanse of the observable universe. The significance of discovering exoplanets lies in its potential to deepen our understanding of our place in the cosmos and to answer fundamental questions about life and existence on other planets. The ongoing exploration of exoplanets allows us to investigate the vast diversity of planetary systems and explore the possibility of new forms of life beyond Earth. Moreover, these discoveries can enhance our comprehension of how planetary systems form and evolve over time. The implications for the search for extraterrestrial life are profound. Exoplanets serve as critical candidates for harboring life and can provide valuable information about the conditions necessary for life to thrive elsewhere. Ultimately, the study of exoplanets enables us to test our existing theories and models regarding the formation and evolution of planets and stellar systems, significantly advancing our understanding of the universe and our role within it. Exploring the vast expanse of our universe has always sparked human curiosity, pushing us to seek answers about our existence and the potential for life beyond Earth. The quest to discover new worlds is not just a scientific endeavor but a philosophical one that challenges our understanding of life, habitability, and the cosmos itself. As we venture deeper into the realms of space exploration, our technologies and methodologies continue to evolve, enabling us to gain insights that were once unimaginable. Recent missions to various celestial bodies within our solar system have provided valuable data about planetary environments. For example, the Mars rovers have unveiled evidence of ancient rivers and lakes, suggesting that the red planet may have once harbored conditions suitable for life. Additionally, missions to the outer planets, such as the Juno spacecraft orbiting Jupiter and the Cassini probe studying Saturn, have revealed intricate details about their atmospheres, magnetospheres, and moons, some of which may also hold the potential for life. The diversity of these environments highlights the myriad ways in which life could potentially arise. The search for exoplanets has further revolutionized our understanding of where life might exist. Kepler's mission alone has discovered thousands of exoplanets, many of which reside in their stars' habitable zones. These discoveries have expanded the definition of what constitutes a potentially habitable world, allowing scientists to consider various factors such as the presence of moons, atmospheric composition, and geological activity. One intriguing aspect of the study of exoplanets is the concept of biosignatures, indicators that suggest the presence of life. Researchers are developing techniques to analyze the atmospheres of distant worlds, looking for gases like oxygen, methane, and carbon dioxide that could indicate biological processes. The potential for using telescopes like the upcoming Extremely Large Telescope, ELT, or the Roman Space Telescope to search for biosignatures is generating excitement in the astronomical community. These observations could revolutionize our understanding of life's distribution in the universe. In addition to direct observations, the field of astrobiology has gained traction, examining the conditions that might allow life to thrive elsewhere. Scientists are studying extremophiles, organisms that can survive in extreme environments on Earth, such as deep-sea hydrothermal vents and acidic lakes, to better understand the limits of life. This research informs our search for life in places previously deemed inhospitable, such as the icy moons of Jupiter and Saturn. Enceladus and Europa, in particular, are of great interest due to their subsurface oceans, which could harbor microbial life. As we look toward the future, the idea of colonizing other planets becomes increasingly plausible. Projects aimed at sending humans to Mars, such as SpaceX's Starship and NASA's Artemis program, envision a sustainable human presence on the Moon and beyond. These initiatives not only aim to push the boundaries of human exploration, but also to establish a permanent human foothold in space, paving the way for further exploration of the solar system and beyond. The potential for discovering life beyond our planet raises profound ethical and philosophical questions. What would it mean for humanity to encounter extraterrestrial life? How would we approach communication and interaction with intelligent beings? These questions are not merely speculative. They are crucial considerations for future missions. Developing frameworks for ethical engagement with extraterrestrial intelligence is a topic of growing interest among scientists and ethicists alike. Furthermore, the ongoing discoveries in the field of exoplanet research challenge our understanding of planetary systems. The presence of unusual planetary configurations, such as hot Jupiters, gas giants that orbit very close to their stars, complicates existing models of planet formation. These anomalies prompt scientists to rethink the dynamics of planetary migration and the influence of stellar interactions on planetary development. The concept of the Goldilocks zone, where conditions are just right for life, is also being reevaluated. Research indicates that life might exist in a broader range of conditions than previously thought. For instance, subsurface oceans on icy bodies could provide stable environments for life, and high-energy environments, such as those found around